So what's the next one? Safety, we've already went over that. What's the next one? Huh? Control logic. This is a really important chapter. This will be for PLCs. We talk about relay logic. So what is logic? It deals with digital. What is logic? Well, we have 5 operations that we can deal with, and then we have what we call combinational logic, which we take the 5 basic logics and we combine them to do more complex tasks. Anybody know the 4 logic functions we have? Somebody started. Go ahead. And normally logic we're supposed to write in uppercase letter, huh? Then we have OR. Then we have the complement of that. We have NAND. We have NOR. And then we have what we call NOT. We're also going to look at 2 combinational logic that we refer to as exclusive OR and exclusive NOR. Those are used a lot in relay. So we call this relay logic. A lot of people will call a ladder diagram, they call the circuits actually relay logic. And that's when we decide how we can hook contacts to perform these 5 basic logic gates. And then how we hook contacts to control the combinational logic. Combinational logic means we do a combination of this, right? Basic rules of line diagram. Is this the same one? Yeah, very important. Signals, decision, action, logic functions, common control, and common control circuit. So we'll start off looking at the basic rules of line diagrams. No more than 1 load placed in any line. So there is no such thing as a true series circuit. We have basic circuits, 1 element series circuits, we could call them that, but there is not multiple loads in series with each other. Now what happens is these relays and these devices operate at a certain voltage. So these are not resistors, these are true loads, right? Resistors can be low, but all they do is heat. So I've got a 1,000 ohm resistor right here, and I put 20 volts across it, then I get V squared over R. If I put another 1,000 ohm beside it, now this guy's getting what? Getting 15 volts, right? At the same thing. So what happens is the power predicts by that by a factor of what? Power varies by the what happens if we have the voltage to a circuit? What happens to the power in the circuit? If we have the voltage in a circuit, what happens to the power in the circuit? So everybody said Watt's law and Ohm's law, right? So let's do a circuit. Let's do just 1 circuit. And let's say I come over here and we'll do a DC circuit. And let's say I start off with 20 volts. And then I'm going to come out here and put a 1K resistor. What would be the power? And we'll call it R1. What would be the power dissipated by the R1 resistor? Get out your calculator, get out your pencil, calculate that for me. Now, of course, here the easiest formula would be V squared over R. And what did I say with this? This is 1K. So you can do the current and everything, but you get the same answer. So one of our power formulas is V squared over R. So I'd say power would be equal to 20 squared over 1K. And what would my power be? No, it's going to be watts. Power's in watts, right? Milliwatts. Okay, so let's raise this up to 40 volts. So I double the voltage. So I come over here, this is going to be 40 squared over 1K. What happened? What is it, 1.6 watts? So what did it do? Well, I doubled the voltage, but the power quadrupled, because you have to understand current and voltage are directly proportional. And power is equal to V times I. So if you double the voltage, what happens to the current? It doubles. So power varies with the square. If you go down, if I half it, what do you expect to see? So let's half it from 20. Let's half it down to 10. So here's 10 squared divided by 1K. What happened? It went down to 100 milliwatts. It varies by a fact. So if you go down, it's 1 over the square. If you go up, it's times the square. So power varies with the square of the voltage. So it means right here, if both these had, if this guy right here required 100 watts to work, and this guy right here required 100 watts to work. Well, up here, let's say this guy right here was 100 watts, right? You understand? And then I hooked something down here that had this, and let's say that was 1K, and this right here was 1K. Well, that would be 100 watts. Now all of a sudden it would be getting 25 watts. And this guy right here would only be getting 25 watts. When it needs what? It needs 100 watts to work. So what's not going to happen? Well, the solenoid's not going to pull in because it don't have enough watts. The light bulb you wouldn't even be able to see anymore. And we're going to do this. We're going to deliberately do this circuit to troubleshoot, to see what happens if we have bad connections in a circuit or something like that, and we unintentionally add additional loads in series. And you're going to say, well, my light's not even on. But what's the problem? Why is your light not on? Because we got 3 loads in series. And now instead of getting over here, the relay's got 2,000 ohms worth of resistance, right? You understand? Relays are not going to come in. And the lights are getting current through them, but they're not producing enough work to do the load. So if I come over here and I put 2 loads in series, neither load's going to work because they're not getting enough power to do the work they need to do, right? You understand? So this is why we never have series circuits in motor control. Not on purpose. We're going to do it on purpose because we're going to simulate troubleshooting, and we'll see what happens. So what happens? We'll switch in one light in series of the relay, and it'll usually hang in there. It won't pull in, but it won't drop out. And we hook up another one, and everything drops out because why? And you won't be able to see the lights on because you're not producing enough watts to do what? Usually see it. No series circuits in motor controls on purpose. Now we can have parallel circuits, but we can't have series circuits. Because here in a series circuit, your voltage is divided depending on the resistance of the load. On a parallel circuit, the voltage is constant, and what divides up is current. So we can have parallel circuits. This is perfectly legal. Because if this guy right here needed 100 watts at 120 volts, this guy here would be whatever watt it needs at 120 volts. It would have no problem, right? You understand that? So the only 2 types of circuits we have in motor controls is we have a single load series circuit, which I'll call a basic circuit to get y'all confused, and we have parallel circuits. And that's it. And how many loads can I put into parallel? Well, I can put as many as L1 and L2 will handle without it blowing a fuse or burning up, right? Everybody understand that? No multi-load series circuits in motor controls. And that's also true of PLCs too, by the way. Everybody understand that rule? Control and solenoids, pilot lights, load indicators, they will connect directly to L2 except in motor. There is only one device that'll have something between the load and L2, and that is a motor starter. And what would be over there? So the only thing allowed between L1 and between the load and L2 is an overload contact for a motor starter, a magnetic motor starter. That's the only thing allowed. All of the loads connect directly to L2. Control relays, which do not have overloads, solenoids, pilot lights, anything that can run, any low voltage, low power device that can run inside the control circuit will be connected directly to L2 except for magnetic motor starters. You understand that? Any questions there? Yes, no? Okay. Magnetic motor starters that have overloads on them, we will have the overload contacts. This has become more popular now. Used to have an overload every phase, but what's happened is they designed it so we only have one reset. So when you hit that reset, you're resetting all overloads anyway. So instead of drawing all three of them, standard practice now is just only draw one. But it's also taking up the other three, right? You understand that? Everybody understand that? And these are wired internally too, so you don't really see the overloads around wired in series. They're actually wired in series on the overload assembly itself. Control devices. Control devices go between L1 and the loads. We can hook control devices in series. We can hook control devices in parallel. We can hook control devices in series parallel. The way we hook control devices does not determine what type of circuit it is. They're control devices. What work does control devices do? They don't do any work. They control the load. They have a function, but they don't do any work. They have no watts, right? And when we talk about electricity, when we talk about work, we're talking about power. These guys are not supposed to dissipate any power. If you've got a light switch at your house that's getting hot, what do you need to do? Replace it. If you've got an outlet at your house that's getting hot, you need to replace it, right? You understand that? Because these devices are not, these guys are not loads. These guys are control devices, and they should have little, almost no resistance. In fact, we shouldn't even be able to measure it. So here's some symbols they give it to. So normally, the book does a very poor job on normally open push buttons. See how close they put the contact. There is a space there, but it's very, very close. I used to like to draw them further apart than that. So normally open push button goes above the terminal symbols, and then normally closed push buttons go below. And they should touch. So normally closed should touch. So normally closed should touch. And then normally open should not touch the terminal symbols. And like I said, this guy, when he draws the normally opens, he just leaves a little air gap right there. Are we okay? So we have a normally open push button. We have a normally open limit switch. Gravity's trying to open it and it is open, right? We have a normally open pressure switch. Multiple control devices can be connected in series, parallel, the way you have circuits. So notice this one right here. This one has to be closed, and this one has to be closed before the relay is energized. What logic do you think that is? And if this one is closed, or this one closes, this relay would be energized. So what logic is that? Or, yeah. So there's our logic. And or. People usually don't have problems with ands and ors. It's when we get the nands and ors and the exclusive ors and nots. Knots are easy too, but what we do in motor controls is we don't number rungs, we number lines. So every wire that runs horizontal, not vertical, that runs horizontal, these get a line number. Every line number, and basically any one that's connected together. So this would be a line, this would be a line. This don't get a line because it's in the same what? Path, right? You understand that? So this would be, we have 3 lines on this. How many rungs? 2. Yeah. So notice on this one we have 2 connections. Over here we only got 1. So this is the same circuit. It's just that we can control it 2 different ways. So when you determine if it's a rung, if we have 1 connection on this side, then it's probably a rung. If we have 1 connection on that side, it's probably a rung. Very seldom will we come over here and do that, even though we could. Everybody okay? So what we do in motor controls is we number lines. Guess what we do in programmable controllers? We number rungs. So rungs are numbered, whether they're parallel or series. So it's a. Everybody okay? Yes or no? Okay, so far. Now what we do, why do we number lines? And just ignore this contact that's vertical right here, because it goes through something. What we do is we number lines. And then what we can do is every time we have a relay controls contacts. Light bulbs don't. Somebody in this class is going to put a cross-reference number for light bulbs. So what we do is we identify, and where can these contacts be at? They could be anywhere within our control diagram. So to aid us in finding what contacts are being controlled by a relay is on the right-hand side of L2, we put what we call a numerical cross-reference numbers. What the numerical cross-reference numbers is the location of the contacts controlled by a relay. We separate in their line numbers. So right now, I'll come up here and I'll look at the first relay. That's a relay because they don't have lines coming out of it, right? It's called CR1. It says it has a contact in line 2. So here's line 2. Here's CR1. That's the name of the relay. So we named the relays, right? You understand that? And it says, okay, this guy's got a contact where? In line 2. Well, you start looking at line 2, and there it is. It says it's got a contact in line 3. Okay, so I get into line 3. I'm sorry, line 2. I missed that. Line 2 is right there. It says it has a contact in line 3, which would be right there, and it says it has a contact in line 4, which is right there. Everybody understand that? This guy, notice they separate the contacts by what? Commas, and then they put them inside parentheses. Most of the time you won't see the parentheses, and we'll show y'all the USD print. Where's the contact numbers for this guy? Huh? That's a loaded question, guys. It's a light bulb. A light bulb don't have contacts. It's the only thing that has contacts are relays. Relays have coils that control contacts. Light bulbs don't control contacts. It's a light bulb, right? How many of us are going to assign contacts to a light bulb? Somebody in this class will do that. This says, this is a relay. How do I know it's a relay? Well, it's a circle, right? It don't have the lines coming out the side. Solenoids don't have contacts. The only thing that has contact is what? Relays. So what we do with these numerical cross-reference numbers is we show the line number that where the contacts that this relay controls reside. So CR2 has a name called CR2. Now these are pretty common. CR2, they're saying it's a control relay. What a control relay is, a control relay is a relay whose contacts are not there. It has no contacts in the power section. All the contacts of a control relay are somewhere in the control circuit, somewhere, and that's why it's called a control relay. Motor starters, magnetic motor starters, and contactors, they'll probably have contacts in both the control circuit, but they're going to have also in the what? In the power circuit. So that's the big difference. Control relays are usually going to be small. They're not designed to handle a lot of current. The loads that they carry are not going to be high power, high current loads, right? So where do I need to look for CR2, which is the name of the relay? Where do I want to look for it at? If y'all got y'all's book, you should find this. 8. So I come down here, I find line 8, and I look for a contact with the same name. There's the contact with the same name. So this relay is controlling that contact right there. And where else do we have a contact for it? Line 10. I come down to line 10. I look for the same name. So it's also controlling that contact right there. Where are the contacts for that guy? The guy got in the square. It says M1. The one in the rectangle, excuse me. The one they got drawn the big box around. Where are the contacts for that? This is an overload. This is the control circuit. And most controls are made out of two circuits. It's made out of a control circuit and a power circuit. You understand? Yes or no? So where are the contacts for this motor starter at? In the power circuit. They don't have any contacts in the control circuit. Those contacts are in the power circuit. Those are starting a motor and stopping a motor. So the only thing that's going to be labeled out here are contacts that are in the control circuit. These are not going to show you the location of contacts in the power circuit. Everybody understand that? So when we drew that diagram a while ago, I showed you L1, L2, L3, and T1, T hooked to the motor, but it wasn't in the diagram, right? You understand, because it wasn't in the control circuit, because those were in the power circuit. So normally when we deal with controls, we have two circuits. We have one that's responsible for controlling the operation, and then we have one that handles the power of the operation. And why do they usually split that into two different circuits? The control circuit is usually a low voltage circuit. And what advantage does low voltage have over high voltage? Safer, which means we can get in this thing, we can troubleshoot it, right? You understand? Have no problem. And then these magnetic motor starters won't be in the control circuit. They'll be over there where? Yeah. But this would be what we're talking about, right? You understand that? So most control circuits consist of two parts, a control circuit and a power circuit. So all we know is this guy has no contacts in the power circuit. In the control circuit. So where's the contacts for this guy? It's a light. It has no contacts, right? Somebody in this class is going to do that. I don't know. So somebody in this class I've never taught a class this size where somebody didn't do that. And there's the ones that don't ask questions, right? They sit back there, and when I say, everybody okay? Anybody got any questions? So this is a more detailed thing. We've added another feature in that this is a what? Normally closed. This is a normally open. This is controlled by M2, and this is controlled by CR2. Right? Everybody follow that so far? So what we need to do is we need to have identified, we need to be able to tell the difference if I'm looking for a normally open contact or a normally closed contact. So what they do on a normally closed contact, if y'all can see this, you can see it in your book, but it says 12 and it's underlined. So it says M2. It has a contact in line 12, but it's got an underline, which means I'm looking for a normally closed contact. So I come over here and look at line 12, M2, and there it is right there. I'm looking for a normally closed. So if it don't have a line under it, we're looking for a what? Normally open. If it does have a line below it, we're looking for a normally closed. Y'all understand that? These are just highlighted. These just have highlights around it to know what we're talking about, how we identify normally close contact. Now, I'm not saying you're never going to get out there and see one that's not highlighted, because somebody might have took a highlighter and did what? Highlighted. Normally, we don't have color on a print. Why don't we use color? Because these are diagrams for one thing, and it would be a lot more expensive to handle. So just about all your prints are going to be just black on white. You're going to be getting a diagram that's sort of like this. It's not this one, and you're going to have to do line numbers. You'll have to do contact numbers. That'll be one of the labs that we'll do. We'll do one as a worksheet, and then eventually this will be on the test. So normally our tests, some of our tests are split into two parts. And then one of the parts will be one of these. It'll be a blank line diagram. It'll have the relays, and you'll have to come up and do what? Fill up the line numbers, and then do the cross-reference numbers, and also wire numbers. We ain't got the wire numbers yet. Everybody okay? And every lab that you hook up, so they're going to give you a wiring diagram. A ladder diagram of a circuit that you're going to hook up. And one of the first things you're going to do for every circuit you hook up is one of the first things you're going to do is do the line numbers and the cross-reference numbers. And that way, it'll be easier for me to figure out, right? You understand? And plus, you'll get that habit. Something popping up on my screen. Everybody okay? Yes, no? Okay. Next. And then we'll go to lab this last time. No, we need to look at two more things. These are what we call manufacturer's numbers. These are not, these are wire reference numbers we're looking at right here. So what we do is we number wires. And while we number wires, it gives us the ability to hook them up. On airplanes we worked in, every wire was white wire. Everyone. So airplanes, if ever in an airplane, you're talking about some wiring. We're talking about wiring. But what they would do on the jacket of the wire, every 6 inches, they would have a wire number on it. So no matter where we was at, we could find that wire. Now, in industry, they don't usually do that because that's a lot of trouble. In industry, what they do is usually the wires are the same color. Out of USL, just about every wire was black, except if it came through a cable. Cable wires are different colors. So what they would do at your terminal blocks and at your relay terminals, that's where they put the wire numbers at. So we had wire numbers where we usually made measurements at, right? You understand that? Every wire that is connected to a common spot gets the same number because they are electrically the same. So notice on this one, usually when we start doing wires, we start in the upper left-hand corner. So on this one, L1 is called 1. So you notice it's 1 all the way down the line. Why is it 1? Because it's the same. It's technically electrically the same wire. So if I wanted to find L1 anywhere in my control system, if I found the number 1 on a wire, I knew that was L1. Right? So I wouldn't have to go all the way back to my transformer. I've got to put my meter lead back here on L1 on the transformer. All I need to do is find what that wire number is. Then what you start doing is you start numbering wires from left to right. So it's left to right, top to bottom. So we go through the push button. Every time you go through a device, you change a wire, right? You understand? So one, we go through a device. You don't connect across that device. Somebody's going to do that. They think they've got to make connections on both sides of a push button. Well, what I use, I say it's the car that's between the bumpers. So you got two bumpers, but the bumpers are not connected together. What's between the two bumpers? A car. Well, what's between those two terminals? A switch, right? You understand? So you don't jump across switches. Somebody in this class is going to do that. They think they got to but we go through a device, and what did it do? It got a different what? It got a different number. Then we come through our control relay, and what number are we up to? 3. Well, what did we do now? They went down all the way down L2 and they numbered it what? 3. Why? It is electrically the same. So if I wanted to measure my line voltage, what could I do? I could find any wire numbered 1, measure to any wire numbered 3, and that would measure my line voltage. I wouldn't have to go to the transformer. In fact, that might be my problem, is that I measure voltage at my transformer, but I've got a broke wire down here somewhere, right? You understand? Well, the voltage is good, right? But it's not good where? So you come over here and this wire's broke right there. These guys are not working. You go up there and measure across the L1 and L2, and you say, well, L1 and L2 is good, and then you move on. Well, it can't be L1 and L2. They both measure what they're supposed to, but you didn't measure where. You didn't measure here where you should have measured, because these two guys are not working, but I could have measured here or I could measure there, right? 1, 2, 3. So as soon as I identify L1, what do? I'll number it. Why don't this guy get the same? Why don't this guy get another number? It's still L1. It's electrically the same. So this wire right here is still number what? It's still number 1. So why don't this guy? So 1, 2, 3. As soon as I identify L1, I'll just go down and number them. As soon as I identify L2, I'll number all these. And then I can come back up here and go what? 1, 2, 3. Then 1, 4, 3, 1, 5. Why don't this guy get a number? It's the same as 5. It's electrically the same. So I can measure it here or I can measure it there, right? 3, 1, 6, 7, 3, right? 1, 8, 9, 3. Sound like learning to count in elementary school, right? But what's somebody going to do in this class? What's somebody in this class going to do? They're going to number every wire. They're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. But if it's electrically the same, it gets the same number. Everybody understand that? So what do we look for here? We learned about line numbers. Everybody okay? We learned about contact, numeric cross-reference numbers. Everybody okay? And now we're looking at what we call wire numbers or conductor numbers. Right? In our class, we're not going to identify wire numbers because we're not going to make something that's that complicated. Next thing we'll look at is what we call manufacturer part numbers, but we'll do that. Manufacturer numbers, terminal numbers that we looked at. We've already talked about a little bit over here. So when you buy a part, it's usually going to have numbers on it. And the problem is it's just about every one of them is going to have the what on it. It's going to have the number 1 on it. So when you hook up your wires, you're not looking for number 1. You're looking for the number 1 on the component you're supposed to be looking for, right? And somebody next year is going to, I hate to tell you all this, but I hadn't taught the class in a long time. Mr. Sanders started teaching it for us. It worked out that I taught it. But every time I've taught this class, I want y'all to make me a liar. Every time I've taught this class, somebody has numbered every line. Somebody has given light bulbs contact numbers, right? Somebody has put a jumper all the way over here, down here, and down here, even though the two terminals are outside each other. Now, electrically, that's okay. It's just that if you was an electrician and you was bidding on a job, somebody would underbid you. Because you'd be using all this wire, and this guy over here would be using a lot less, right, doing the same job. Here it's electrically the same. So if you've got a wire that you're running, if you're running 2 and they're side by side and you're running down here, I'm just going to say, that would be a more efficient way to do it. I'm not going to make you tear down your circuit and redo it. We're going to use what we call a two-terminal rule, which means it's on the power supply, no more than 2, one on L1 and L2. And then after that, no more than 2 jumpers on any plug. And you'll find out, you'll learn that you can do what? You can figure out how to jump and do more than 3, more than 2. problem is we're using banana plugs, and we're dealing with gravity, right? Understand? And we've seen it. You put two of them down here, and now you barely touch it, and one of them falls out on you. So these are not screw terminals we're using. We're using banana jacks, which makes it easy. It means we can wire a lot faster, and we don't strip terminals out or strip the like we've had these guys. Like I said, we were the original company of college that set these things up, and I can't tell you how old they were. But everything on there still basically the same, except the only thing we're doing is most new installations is not using 120 volts. Most new installations are using about 26 volts for their control circuit. And why? It's below 50 volts. And what's 50 volts? Yeah, the 70E standard has set 50 volts as being the lethal voltage, even though it don't mean you can't get killed below 50 volts. It's just that's the standard they set. So as soon as you get below 50 volts, it means you got to start wearing special PPE, right? Anything below that, it depends on your company. So, all right, guys, let's go ahead and take a break. We'll come back, and if you don't have your lab, we told you about the lab, right? We're going to inventory the kits. If you don't have your lab book, that's okay. I'll give you a checkoff sheet where you can check off it with your team. If you're working with a member, and why you need your lab books is they show the parts, what they look like. I'll bring some extra lab books out here if you're working with a partner, so that way you know what you're looking for because they give you an actual picture. We're using the NEMA standards. They have two kits they put out. One's using the ICE, the International Standard symbol. We're using the National Electrical Manufacturer devices. So if it gives you two pictures, and one of them's NEMA and one of them's IEC, you need to use the NEMA picture. That's the one we have. Here's the inventory sheet. Here's lab forms, guys. Y'all need to fill out the part that y'all need. We'll go over the actual procedure. So what chapter is this?